Way to go.
Chocolate chips
Um,
to the cookie.
And then we went out.
I mean, if you were missing for track, that'd be one.
And then do something with me.
I'm not even
It
good
just,
at
that's just the day we just have to do. All right.
What day?
Is anybody else gonna be gone on Tuesday? So Carrie will miss that too.
I'll be gone.
Carrie, the
Summer-
Carries.
Wait,
are-
this
Carrie
coming
Square.
Tuesday?
This next
Like weekend,
Tuesday,
Monday, Tuesday?
yes. It's
Yeah,
right next
Monday.
Tuesday.
What's Tuesday?
And I'm sure you'll probably leave.
Monday. 'Cause we're going to Pine, and we play at 5.
What's this water?
Well,
And the boys like to be there like an hour.
But I thought we weren't.
do they,
Oh, we might not.
But we're still leaving. We're still.
you would surely leave by 1, which would be halfway through anyway. So you, so you can be here for part of it. So you'll be here for part of it.
Yeah.
See what's the latest you can stay before you have to. All right.
But if he doesn't,
All right.
Not
So,
everyone does.
shh.
I'm not bad.
All right. Let's.
I like track.
All right. Let me run through a couple of these, and you had access to the answer book, obviously. Looks like you had some things down. Now, pictures. Pictures are very important. Every one of these, where it says find the area of a region, and some other problems we'll be doing that involve regions. Okay, they usually always start with a region. Let R be the region. On the AP test, it's always let R be this region, let S be this region. And they define it. A lot of times they give you a picture, sometimes you have to draw a picture, but you have to have that as part of it. On our quiz, there will definitely be sketches that you will have to do. So the first one I want to look at is number 17. And then was 29 part of that as well?
Yep.
So they give you the region defined like this, but they didn't draw it for you, right? And so you need that. Even if it doesn't say draw the region, I think it did. I think that was part of the, it says sketch the region bounded by the curves and then evaluate it. Now, on the first ones, they wanted it in terms of x, which means what? On 17, it was like f of x minus g of x and then dx, and then these was in terms of y. What's the difference?
Well, one is split up this way.
Vertical strips, horizontal strips, right? Now, on the quiz, I may have some of the problems where I tell you do it with vertical strips. Some where you have to do it with horizontal strips. And then some may just be find the region, and you can choose whichever one you think would work best or which you'd rather do. Okay? Now, quite honestly, there are going to be some that can only be done one way. And there are going to be some that can, be done both ways, but one might be easier than the other. And there could be some where they're about the same. And this, to me, would be one that's about the same. Okay? So as you look at this region, and let's do the first one in blue here. And so we're doing vertical strips on 17. So we draw in a vertical strip, and we talked about top minus bottom. So it would be the integral from, we'll do that in a minute. It's the top y value. What's the y value right here? Square root of x, right? It says it right there. Y equals square root of x. So it's going to be square root of x minus the bottom y value, which is 0. You don't have to put the 0, but I like to do it. I'm in a habit to do it just because I want to reinforce the idea of top minus bottom, right minus left. Okay, and that integral goes from, because the strips fill the space from 0 to 4. So we go 0 to 4. You type that in your calculator, and I think you got 16/3. Is that what it was for that one? Okay, so that's that area. All right. Then you go to number 29. They want you to do the same region, but with horizontal strips. So that means like this. So now we want to take this right x coordinate minus the left x coordinate. So what's the right x coordinate? 4. What's the left x coordinate? Well, it's the x coordinate from the parabola, so we got to get x equals. So we have to square both sides. We get x equals y squared. So the right x coordinate is 4. The left x coordinate is y squared. We stick on the dy, and then it's from this point right here is the point 42, and so the strips fill the space from 0 up to 2. And you type that in, and you get exactly the same answer which you should. It's the same region. So really have to understand that you have to be able to graph the region, and then you have to get this idea of horizontal vertical strips. Now, what does it do when we do when we do right x coordinate minus left x coordinate? What's that giving us? Yes, it's a positive, but what else? What does that represent? This right x minus this left x. What of the horizontal strip? The length of the horizontal strip, right? So when we say right x minus left x, we're saying the length. Now up here, this x minus this x is littler because this x is over here farther, it's a bigger number. So right minus left is a littler number than it is down here because they have different lengths. All right, and then where's the width come in? The dy. So the right x minus the left x, that gives me the length of the strip. This gives me the width of the strip. Length times width is area of the strip. And then what's the integral do?
Where? Like the definite
One word, starts with A.
area.
No. Adds them up. That's what I want you to think of. It comes from sigma. It's an infinite number, yes, but this integral adds them up. So this is the length of the strip times the width of the strip, making the area of the strip, and then the integral adds up all the strip areas from 0 to 2. Okay? That's why this works. So that's this top minus bottom, right minus left. But it's just an extension off of area where we were adding up rectangle areas. That's what we're doing. Each strip is like a rectangle, and we're adding it up. Okay, we go to the next one. Now, the next one's a little more complicated region. They gave you the graph this way. How are you graphing that on your calculator? Because you have to be able to graph it. Now, quite honestly, when this book was written, they assumed you're doing this by hand and that you just knew that this is a sideways parabola. It's something you learned in Algebra 2. When it's x and y is squared, it's a sideways parabola. So it's just a sideways parabola shifted instead of down 4, it's shifted left 4. So it's a sideways parabola shifted left 4. Okay? But how could you do it on your calculator? Because you're going to have to be able to do that. Solve it for y first, right? So if you want to put this into your calculator, you would solve this for y first. So you'd add 4, square root it, and when you square root it, you have to do plus or minus. Now when you put that in your calculator, you have to put both of those in separately. You have to do the square root of x plus 4, and you have to do the negative square root of x plus 4, y1 and y2. That way you get the top half and you get the bottom half. So I think maybe we talked about that a little bit on Wednesday. So this curve here would be this, and this curve down here would be this one. Okay? All right. So now in 23, we were supposed to do it with vertical strips. Now what happens when you try to do this one with vertical strips? No, that's not true because we're not going to be taking the square root of a negative number because our x is, the farthest x gets over here is negative 4. Negative 4 plus 4 is 0. So I don't think that would be a problem. Well, let me draw in a vertical strip. That's not one function. See, that's what we were just talking about. The top half of the parabola is that function, and the bottom half of the parabola is that function, right? The problem comes in because of right here. What do vertical strips look like over here? What's different? Why do we have to split it? Different top function. The region on this side of the y-axis, the top function's a line. The bottom function is the bottom part of the parabola. Over here, the top function's the top of the parabola, and the bottom is the bottom. Okay, so you have to have the same top and bottom throughout the whole region, or you have to split it into parts. And there might be some on the quiz. I could give you this one and say, do it with vertical strips, just like problem 23. Then you would have to split it into pieces. Okay? So let's set up the first piece. So let's do this first piece here. Tell me what to write. Top y. Well, I usually put that in at the end. Top y minus bottom y. So root x plus 4,
plus
and it'd be minus a negative root x plus 4, which will end up being a plus, right? But it's top root x plus 4 minus negative root x plus 4. Which ends up being plus, which would just be 2 root x plus 4. But that's just how you want to type in calculator. And then it goes from, the strips fill the space from negative 4 to 0. Plus, now we do the next region. Top curve, the top y, 2 minus x, minus the bottom y, so it'd be minus a negative root x plus 4, which again will end up being a plus. dx. And that goes from 0 to 5. And you have to find those intersection points. I label them all for you. But you've got to be able to graph that. You've got to be able to find those intersection points. You've got to be able to do all that. And so you type that. So you type this all in, and it's what? 125 over 125 over 6. Is that what it is? Okay. When you get all done. But all the points come in, number 1, having the sketch, and number 2, having the proper integral set up. You know, and then maybe 1 point for that final answer. But all the points come in getting that set up. All right, now, in the blue, we'll do the number 35, which is a horizontal strip. So there's a horizontal strip. Now we have to split this apart. No, all the horizontal strips that you possibly can draw in here are going to have the line on the right and the parabola on the left. Now, is the parabola broken into 2 pieces this time? Not when we're doing horizontal strips, because when we're doing the x on the parabola, what is the x? We already have it. The x is y squared minus 4. Okay? So what we need is the x for the line. So we got to solve this for x. So we add x over to that side and subtract the y over, so we get x equals 2 minus y. Right? So the horizontal strips, so the length of a horizontal strip is the right x, which would be 2 minus y, minus the left x, which is y squared minus 4. Right? I mean, I'm looking at some of your answers at 35, and I'm seeing, you know, I'm not seeing this, but I'm seeing some simplified version of this that probably I don't know where it came from, but you just got to make sure you know how to get these things set up. And then that's going to go from what? -3 to 2. The horizontal strips start down here at -3, and they fill the space all the way up to 2. And you better get that same answer. Okay? All right, let's talk about number 3 here. Here's number 3. Number 3 was talking about this region that you were given in the exercises. Figure 4, region number 2, I believe it was called. And again, this could be a region I give you. That's kind of hard to describe. They give you the parabola, this first parabola. They give you the line y equals 1, y equals -1. They give you the line. Okay, it looks like this. Now, look at part 3. Here's what they were trying to get you to do in number 3. It's all about splitting it up. So on number 3A, okay, Mandy, read that to me. Read me what A says. You got your book, Andy? Sydney, you got yours there. Go to number 3. That's what you get for getting your book out early, being prepared. You get punished. That's not fair. All right.
Maybe do the whole thing.
Just part A. Yep.
Find the area of the region bounded below by the x-axis.
Stop. So bounded on the bottom or below by the x-axis. Okay, go.
Above by the line y equals 1.
So it's bounded above by this line. Okay.
On the right by line x equals 1.
So it's bounded on the right by x equals 1, which would be this line right here.
On the left by the curve x equals 1 minus x squared.
Which is this parabola. So they have just described to me in part A this region right here. Okay? They said bounded below by the x-axis, bounded above by y equals 1, bounded on the right by x equals 1, and bounded on the left by the parabola. That's the region. So you were to use a vertical strip in that one to do that. So it would be top minus bottom, top y minus bottom y, and do that. Then in part B, they describe this region. So it's a very similar description. And then you find that area. And then in part C, they describe the rest, which would be the red region here, which is basically just a triangle. You add up parts A, B, and C, and that should give you the whole region. So if I had given you this problem and it said, use vertical strips, this is how you would have had to do it. You would have had to divide it into those three regions. Now, what they did in the exercise in the book is they actually used horizontal strips. Horizontal strips would be the way to go on this problem, right? Because horizontal strip with the right edge would be on the line all the time, and the left edge would be on the parabola all the time. And so the smart way to do this one would be with horizontal strips. So the purpose of part 3 was just, or question 3 was just to get you to see, what it looks like in a problem if you have to divide it up into pieces. Okay? And be able to draw the regions that are described with all those different curves. Some of them are easy to get, some of them are easy to see, some of them are not. Okay, here's a curve right here. I want you to do this on your paper, do it right on your homework paper. Here's an equation. I want you to find the area of that using integrals. I want you to set up an integral that will give you the area enclosed by that region right there. And hopefully everybody knows that's the equation of what?
Circle.
A circle centered at the origin, radius 2, right? So draw your picture, set up your integral, and see if it gives you that actual area.
What?
Set up an integral.
I like those.
Alright. So the area should be 4 pi, obviously, right? Area of a circle is pi r squared. Radius is 2. 2 squared is 4. 4 pi, right? So the area depth. Well, but I didn't want you to do that, but I mean that certainly should be the answer, right? Because it's a circle, right? It's a circle. So the area enclosed by that. All right. So what do you have to do then? Draw it. Then what?
So, depending on which one you're gonna do, like horizontal, you have to solve for it.
And in this case, it doesn't matter, right? Because it'd be basically the same thing. So we're going to have to draw it. We're going to have to solve. I've chosen to do y. If I have a choice, I do vertical script usually. So I'm going to solve it for y. We got to remember plus or minus, just like there's a top and bottom half of a parabola. There's a top and bottom half of a circle. Okay? And so the top half is square root 4 minus x squared. Bottom half is negative square root 4 minus x squared. And so your strip, top minus bottom, would simply be square root 4 minus x squared minus a negative square root 4 minus x squared. And it would go from the strips would fill the space from negative 2 to 2. And so there is a really complicated way to do the area of a circle compared to, of course, the formula for pi r squared. What's kind of interesting, because our calculators, I think this is actually part of your homework in the LH packet that I'm going to give you here in a minute. So this will help you to do this pretty easily. What would be the general equation of a circle, the area of a circle? Instead of this specific circle with radius 4, what would be the radius of any circle? What could we write for the radius of any circle? R, right? Oh, I forgot the x squared. So the equation of any circle would be x squared plus y squared equals r squared. Well, how would that change this integral down here?
R squared.
So it would go square root r squared minus x squared. And then, so wouldn't there just be a 2 in front of it? Right? Just be a 2 in front of it. And it would go from negative r to r. Try that in your calculator. That's one of the cool things about CAS, the computer algebra system, is it'll do this with letters in it. So now go ahead and put in that integral from negative r to r. And it should give us the area of a circle. It should give us pi r squared. Now I'm afraid it might not quite. What's it give you? It gives you pi times r times absolute value of r, which is pi r squared. And what this is saying is, because we didn't tell the calculator that r
It's always positive.
is always positive. R could be negative, and then all of a sudden they'd say, well, if r is negative, then we'd want to flip that around. Okay? So, because if the radius is negative, then all that would change. So let's do this. Go back to that integral you had. Go back to that integral you put in and do a vertical bar and do r greater than 0 at the end of it. Grab that integral again and do vertical bar and tell the calculator that r is always positive, and then you should get pi r squared.
Where would you do that? Like after the dx?
After the dx, that'd be all the way, yeah, that'd be after the dx. Yeah, after the dx part. Okay, and then it gives you pi r squared, which is kind of cool. It gives you that formula. So we set it up and we create it based on this idea of area and strips, and then it comes out to give you that. All right. The next thing we want to look at here is another thing that's in this section 7.1. And so you probably need your notes out here to, because you're going to want to jot down some stuff here. And while you're doing that, I'll show you an example of what we're trying to do here. All right. But as you can see on the title of this, we're gonna want to talk about arc length. Arc length. Now, you've heard arc length before in advanced math class when you were talking about circles and radian measure, and you did it geometry. You know, the length of an arc around a circle. But we're not talking about just on a circle here, we're talking about on any curve. Like the example I have on the board here is a parabola, right? What's the length of that blue piece of the parabola? Now think about if you had to measure a length on a curved surface, like if we pulled this trash can out right here and said we want to measure the perimeter, the circumference of the trash can, what would you do? Get a piece of string, right? And then lay it around and try to get it, and then so you could straighten it. Because the only thing we know how to measure length of is straight lines, right?
Radius rather than trash can.
Well, because you know the formula, since you know it's a circle, you can do radius, you can do circumference equals pi times diameter, or 2 pi r, right? And so, but that's only for a circle. So if we had this curved surface, if I gave you a piece of paper with this parabola on it and some string, you could lay the string around it, right? And then you could straighten it and then measure it. But the only way to really measure a length is straight lengths, okay? So it'd be great if we could take this parabola and straighten it, and in a sense, that's exactly what we're going to do, okay? Now, I've got the red line drawn there. I can measure that red length, and they have right down here. Is that a very good approximation to the blue length? Probably not. How about if I measured those two red lengths and added them up?
It's getting close. Oh, wow.
We'll go to 11. But, right? Look familiar?
Yeah.
Very familiar. Matter of fact, yeah, unfortunately. You're supposed to be a little more excited about that, but it's Friday. Okay. So, but listen, see, I mean, and now go back. All of the kind of the major kind of discoveries, all the different things that we've done in calculus have had this kind of look to them, right? Don't know how to do slope at one point, but we do know how to do slope at 2. So we'll do slope at 2 and let the two get really close together. Don't know how to do area under a curve like that, but we do know how to do rectangle area. So let's do a whole bunch of rectangles and do an infinite number. Don't know how to do length of a curve, but we do know how to do length of a straight piece. So let's turn that curve into a bunch of infinitely small straight pieces and add those up. And eventually we'll get closer and closer to the right answer. Okay, so we can skip a lot of the preliminary stuff and we can jump right into trying to find a formula for this. So here's what we want to do today. Here's what we want to come up with. All right, we've got this curved piece of graph. We want to find the length of it. What we're going to do is we're going to pretend that it's straight for little tiny pieces. And then we're going to add up all the infinite tiny pieces. Well, what are we going to use to add up the tiny pieces? Integral, right? Sigma, which then with an infinite number turns into integral. So we're going to use an integral to add up all the tiny lengths. So what we need to do before we can use the integral to add up the tiny lengths is we need to get a way to write one of the lengths. Okay, so this is going to represent one of the lengths right here. We'll just call it S for like arc length or string or sigma or for Sydney. Yeah, whatever. Okay, so we'll let S be this length right here. Now, how can we find that length? Well, we know to do the length, we can break it up into these two pieces here. Okay, make it into a right triangle. So to find that length, now we need to give a name for these. Now, what could we call this piece across here? The width, and of course, as those lengths get tinier and tinier, this, of course, is going to shrink and shrink and shrink, right? How about we call it dx? Could call it delta x, but we know eventually, once we do an infinite number of them, that's going to go to nothing, which is eventually going to be our dx. So let's just call it dx right off the bat. Make things easy. And what can we call this here? Why don't we call that dy? Because it really comes from change of x and change in y. And that's what that is. So we call that dy. And of course, dy over dx would be like slope. Well, isn't that rise over run? I mean, those would make sense to do that. And s is going to be the length of the hypotenuse. Now remember, this s is going to be getting smaller and smaller and smaller, isn't it? Because these points are going to be getting closer and closer together, right? Because these lengths, we're gonna do tinier and tinier little segments that we're adding up. Okay, so the length of that one piece of segment would be s squared would equal dx squared plus dy squared, right? So we can start with that. And so s, of course, would be the square root of that. And it's positive, it's gonna be a positive distance, so we don't have to worry about plus or minus. Okay, so that's the length of one little tiny piece. And of course, at the end, we'll throw the integral on there, and that'll add up all the tiny pieces. Okay, that'll add up all the tiny pieces when we throw the integral on. Okay, but we just want to write the equation one. But when we throw the integral on there, think about this now. Any integral always has to have this dx piece at the end. It has to. Okay, or it's not an integral. It has to have that dx piece. We don't have that right now, so we can't just throw the integral onto this. But there are dx's in there. So we need to do some fancy algebra to get the dx out here like it's supposed to be. And no, we can't just square root each of those individually. That doesn't work. We can't split up a plus sign there. Okay? All right. So we're going to do some fancy algebra here. So try to stay with me on this. First thing I'm going to do is I'm going to make this dx squared plus dy squared over 1. So I haven't changed anything yet, right? And inside of there, I'm going to multiply that by dx squared over dx squared. Which means I just multiplied it by 1, a fancy 1. So I haven't changed anything inside of there. So, okay, so this is still equivalent. All right, so that length, that little piece of length is this. So now I'm going to do something that hopefully you'll think's okay. If I had 3 over 1 times 5 over 7, couldn't I make that, couldn't I just multiply the 7 times the 1 over there and leave the 5 out there? Wouldn't that be the same thing? Okay. Oops. Well, I want you to be convinced. Isn't that the same? I mean, this is 15/7. That's still going to be 15/7. I just multiply the 7 over there on the bottom, leave the 5 over there. So I'm going to do the same thing here. So I'm going to basically bring that dx squared into on the bottom there. Okay? Now, once I have that dx squared on the bottom there, can I split these apart? Right? Okay, so the next thing it'll be is I'll have a dx squared over dx squared. And then I'll have a dy squared over a dx squared. And then it probably should put that in parentheses. And then I'll have this dx squared kind of sitting out here by itself. That's kind of like the top. Right? Kind of like the top. So the bottom I brought in there and then split it apart. And the top I just kind of left up there. Okay? Okay with that? Now I notice that I've got this square root here with the parentheses multiplied by this other thing. Now I remember something about square roots. If I have square root of 8, I can write that square root of 4 times square root of 2. I can split it apart into 2 separate square roots like that, right? So if I've got these two things multiplied, can I split that into 2 separate square roots, right? Yeah. Now what's going to happen to this second thing? I'll have square root of dx squared, which is dx, which is what I wanted. So I'm going to end up with, now we can simplify this as we go here too, right? This is 1, and then this is going to, we'll just leave it for a minute, dy squared over dx squared. And then we're going to have this dx sitting out there, which is what we want, right? One last thing I want to do here with a fraction, if I have 2 squared over 3 squared, right, that's 4/9. Isn't that the same as 2/3 all squared? Isn't that the same thing? So I have something squared over something squared, I can just put the fraction all squared. So I can write this as square root 1 plus, and then this could be dy over dx, all squared, and then the dx right there. Now, yeah, dy over dx is what? Well, it's derivative, but it was slow. Let's first talk about this, right? Delta y over dx would be slow. But as we do an infinite number of these segments, these 2 points, what? Become 1. And what happens to slope between 2 points is it become 1? It's derivative, what you just said. So, as I let these segments become an infinite number of segments, the dy over dx here does become y prime. It becomes derivative. And then we throw on the integral to add them all up, and we end up with a neat little formula here for the length of a curve. So here's what you'd want to put. So the length of f of x from A to B is going to be the integral from A to B of the square root of 1 plus, so we'll put f prime of x squared, and then the dx. And that is our result. And hopefully that makes sense where that came from. So it's not just some made up random formula that you use, but you can see where it came from. It simply came from Pythagorean theorem, and it came from the same concept that's gotten us every other major discovery we've used in calculus, is approximating and then doing it for an infinite number of times or small pieces, and then some fancy algebra in here, okay? But not that fancy. I mean, it's not that big a deal. To that formula again. So what's that look like as an actual problem? So if I was to give you